This has led some scientists, like the renowned Avi Loeb, to ask a provocative question. Is Atlas hiding a nuclear heart? A self-powered engine? If he's right, it could rewrite everything we think we know about the cosmos. Or perhaps it simply exposes just how little we truly understand about the icy relics that wander between the stars. So, what is the truth behind this forbidden glow? Let's break down the evidence. When Hubble got its first good look at 3I Atlas, it didn't find the usual comet signature. You know the look, a bright core with a beautiful tail of dust and gas streaming away from the sun. But Atlas was different. The brightest part of its fuzzy atmosphere, its coma, was pointing asterisk forward asterisk, directly into the oncoming solar wind. At first, astronomers thought it might be a trick of perspective, an optical illusion, but the imaging teams got to work. They traced the surface brightness profile right across the object's head and found a clear, undeniable asymmetry. The peak intensity, the brightest spot, was sitting ahead of the nucleus, not trailing behind it. This just isn't how sunlight works on comet dust. Normally, the brightest region is just behind the core, where the sun's rays hit the densest cloud of freshly ejected ice and rock. But with Atlas, the brightness peaks on the sunward side and then drops off sharply behind it. It's like seeing a speedboat's wake forming in front of the boat instead of behind it. It just doesn't make sense. The team then mapped the phase angle. That's the angle between the sun, the comet, and us, the observer. They ran sophisticated scattering models, trying to see if there was any way that forward reflection could explain this bizarre effect. Maybe the dust was acting like a strange kind of mirror. The numbers just didn't add up. Even when they calculated for the most favorable geometry, the coma's optical depth basically, how thick and dense it is, was far too low. The dust was optically thin, meaning it was too sparse to bounce sunlight forward with this much strength. To produce that bright forward glow, Atlas would need either a tremendously denser dust cloud or a much larger, more reflective body at its core, neither of which matched what Hubble was actually seeing. There was no anti-solar tail pointing away from the sun, just this faint, steady glow facing into it. And the nucleus itself, buried deep inside that forward haze, was far too dim and small to account for the light by simple reflection. The imaging teams double and triple checked their work, looking for instrumental glitches or artifacts. The particles were too few and far between to act like a giant cosmic mirror. And the nucleus itself? Hubble's powerful lens couldn't see a single bright point of light. Instead, its surface brightness profile put a hard upper limit on the nucleus' S size, no more than 4.4 kilometers in radius, and probably a lot smaller. That S less than a quarter of the size required if the light was just bouncing off simple rock and ice. Independent measurements from ground-based telescopes like Palomar agreed. Most of the light wasn't coming from a big shiny core. It was coming from the dust, but there wasn't nearly enough dust to explain the brightness. Think of it like this: if you crushed a mountain into fine powder and scattered into space, the combined surface area of all those tiny grains would reflect far more light than the solid mountain ever could. But even with that effect, The dust around Atlas was too thin to match the glow we observed. The numbers held firm, even as scientists tweaked their assumptions about the albedo, the reflectivity of the material. It didn't matter if they assumed the dust was dark as charcoal or bright as fresh snow. The required nucleus size remained stubbornly high, far above what the actual images allowed. Hubble's high-resolution imaging was specifically looking for that telltale point source, the signature of a large, reflective core. They found nothing. Advanced fitting techniques, which have been tested on dozens of known comets, set a strict upper bound. The nucleus had to be under 2.8 kilometers in radius. Meanwhile, older models that convert brightness to size kept giving those huge estimates 10, 15, even 20 kilometers. But those models only work if the coma is thick and opaque. Here, the coma was barely a whisper. Its particles were scattering some sunlight, sure, but not nearly enough to explain the total signal. The math simply refused to budge. Too little dust, too small a body, and yet way too much light. The only way to reconcile these conflicting numbers was to accept that something else, something other than scattered sunlight, was contributing to the glow. The standard Comet playbook just didn't fit. The case for a hidden internal energy source grew stronger with every failed calculation. And then there's the trajectory. This isn't just about what Atlas is doing, but where it's going. This object didn't dive into our solar system from high above or sweep up from below. Its entry angle is almost perfectly flat, just 5 degrees off the ecliptic plane. That's the same flat, spinning disk where all the major planets, from Mercury to Neptune, make their orbits. Most interstellar objects we've detected arrive at completely random angles, slicing through the solar system like stray bullets fired from across the galaxy. But this one is gliding in nearly parallel to our planetary highway. It's moving retrograde against the flow of the planets, but it's on the same road. Statisticians immediately ran the numbers. What are the odds of an interstellar object arriving this close to the ecliptic plane by pure chance? The answer is staggering, about 1 in 500. That's not just rare. It borders on unnatural. The ecliptic is an incredibly thin slice of an otherwise vast three-dimensional sky. If interstellar arrivals were truly random, the vast majority should miss it by tens of degrees. Yet here we have an object with an inclination of 175.1 degrees, just 5 degrees shy of a perfect flat path, but moving the wrong way. This peculiar alignment isn't just a geometric curiosity. It has real consequences. This specific trajectory sets up a grand tour of our solar system. It steers 3i Atlas on a path that takes it past Venus, then Mars, and then Jupiter. It's almost as if it's been programmed to sample our system's main attractions, one by one. The combination of its unexplained internal glow and this highly improbable, planet-hugging trajectory is forcing astronomers to consider possibilities that were once confined to science fiction. Is this an artifact? A natural phenomenon we've never encountered before? Or is it something else entirely? The mystery of 3i Atlas is only just something strange is passing through our solar system. It's called 3i Atlas, and it's not behaving like anything we've seen before. Its path isn't a random crash or a scattered trajectory. It's a precise tour, laid out along the very same corridor our own spacecraft used to visit multiple planets. Space doesn't do symmetry, not naturally. Yet every calculation, every model of this object's path keeps pointing to this razor-thin plane. In a solar system built on orbits, this is the one path where you can see everything. Mars is getting the closest look. On October 3rd, 2025, 3i Atlas will pass just 28 million kilometers from the red planet. For a few hours, Mars-based orbiters will have a direct line of sight, even as we on Earth start losing the object to the sun's glare. But that window won't last. By October 4th, it's too close to the sun for us to see clearly. The power required for an Earth-based mission is far beyond what any of our current rockets can provide. Even launching from Mars, which would have been our best shot, is no longer an option. Those launch windows are already closing. The only plausible, though highly unlikely, intercept could come from the Juno spacecraft at Jupiter. It would need a perfectly timed maneuver, and even then, it would only get within 27 million kilometers of the target. With every hour that passes, the gap grows. No matter how fast we react, this object is always one step ahead. But while it was visible, our telescopes got a good look. Spectrographs aimed at 3I Atlas caught more than just scattered sunlight. The signal split into a chemical fingerprint of ancient materials: water, ice, silicates, and complex carbon molecules, the very same blend found in the oldest meteorites. But the chemistry held a surprise. The spectrum was a perfect match for the dust from the Tagish Lake meteorite mixed with tiny water ice grains. That's a recipe older than the sun itself, forged in the cold primordial cloud before our solar system even formed. The surface of this object told its own story. Hubble's images tracked dust streaming from its sunlit side, but the amount was surprisingly low. It was losing mass, but not much. Over 6 months, the surface would lose just a few centimeters of material, far less than the meters of ice and rock that most comets shed as they near the sun. Some teams on the ground calculate even lower rates, suggesting a crust that's barely eroding at all. Thermal models back this up. The cloud of dust and gas around it, the coma looked warm, but not wild. There were no jets, no violent outbursts of gas, just a steady, low-key haze. The water ice on its surface was staying put, barely turning to vapor, while the dust cloud remained incredibly thin. There just weren't enough particles to scatter much sunlight, and not enough heat to drive the spectacular show we expect from a comet. So, we have this ancient object. Its surface is unusually quiet, and the energy it's giving off just doesn't add up. For something this old, the warmth is out of place, and the lack of erosion is a real head-scratcher. This is where things get really interesting. Harvard astrophysicist Avi Loeb looked at these numbers and saw a completely different answer. But the dust is too thin to be a good mirror, and the object itself, at just 4 to 11 kilometers wide, is far too small to reflect enough sunlight to be this bright. So, Loeb asks a provocative question. What if the light isn't from the sun? What if it's coming from within, from a nuclear heart, radiating heat through a thin crust of interstellar material? This isn't just wild speculation. Loeb's model makes specific testable predictions. If 3I Atlas is powered by a nuclear source, its brightness should hold steady as it travels through the inner solar system, completely indifferent to its distance from the sun. No comet does that. A comet's glow flares up as it gets closer to the sun's heat and fades as it speeds away. A constant glow would mean the energy output is dwarfing anything natural for an object this size. If this is true, then what we're seeing isn't a comet at all. It's technology. The kind that's built to last, to travel, and perhaps to observe. Loeb's hypothesis is bold, but it can be tested. If the object's glow dims with distance, like a normal comet, the nuclear idea falls apart. But if its emission remains stubbornly steady, then the mystery deepens. The next round of observations from Mars orbiters, from Juno, from any telescope that can catch a glimpse as it moves away, will be crucial. For now, the possibility hangs in the balance. A nuclear-powered visitor, hiding in plain sight, waiting for the data to decide its true nature. So to recap what we know, Hubble and JWST data confirm 3I Atlas has a steady, forward-facing glow with an optically thin dust cloud. Its body, measured at 4 to 11 kilometers, is far too small to reflect enough sunlight to account for its observed brightness. Over 6 months of tracking, its surface has lost less than a millimeter of material. Spectroscopic analysis reveals ancient water, ice, silicates, and organic molecules, all at unexpectedly warm temperatures. And then there's its trajectory. Just 5 degrees off the main plane of our solar system. It's making close passes by Venus, Mars, and Jupiter, a flight path eerily similar to the ones we designed for our own deep space probes. Its closest approach to the Sun is conveniently hidden from our view. Key questions remain unanswered. What is the true source of its energy? Is its path a sign of intelligent design, or just an astronomical coincidence? What is clear is that 3I Atlas defies our current models for comets. For now, it stands as one of the most puzzling objects ever observed entering our solar system, challenging us to rethink what might be possible out there in the cosmos. Thank you so much for joining me on this deep dive into the mystery of 3I Atlas. What do you think it is? Let me know your theories in the comments below. If you enjoyed this journey to the edge of science, don't forget to like, subscribe, and hit that notification bell so you don't miss our next exploration. See you next time